I am now going to talk about wind energy, again with reference to India in particular, but of course, technology part is common. Basically, this is a wind turbine mounted quite high. A wind turbine mounted high will have mounted high will give rise, and you take the power, wind turbine will produce power and you take it to the inverter. Remember, this will be DC power, again both solar and wind produces DC power. You connect it to inverter and then feed it to grid. This is the grid. More wind will be produced if speed is higher. This is a typically wind turbine, the tower. This is of course the what is it called, the arms of the wind. This is the one which is done at a specific angle such that as the wind flows, this will rotate. As it rotates, this is the mechanism which will convert this rotation, pushes it to generator through the gears and all that, and will give rise to the current, which is then going to be taken. Why is brakes put? If for example, storms are coming and therefore, very high speed wind, if you let it run free, it will run at such a speed that it will break. Mechanical strength is not to go beyond a certain speed. So, you put a brake that will lock and it will not rotate. There is of course, gearbox is used and there are anemometer and all that to track this speed and the controller, and then the power goes from onto the tower out here. So, this is the basics, it is a rotor blades, they are called rotor blades, shaft and generator. So, this operates very much like your aircraft wings. One side of blade is curved and the other is flat. Wind flows more quickly through the curved edge, creating a pressure difference on either side of the blade, pushing the air in order to equalize pressure difference, causing blades to turn. They are mounted on a tower. Tower is 100, today even higher than 100 meters, and this can be mounted on ground. Today it is mounted also in the ocean, and then this is a generator turning blades which will typically rotate around 1500 rpm, plus of course, based on the speed wind speed, it will keep rotating higher or at a higher speed or less speed. So, amount of power generated will vary quite a bit. So, it is not a constant DC, it is a DC, but keeps varying quite a bit. This is a typical deployment, for example, of some of the windmills. If you see, the best windmills are today at 128 meters, this S128 is around 128 meters height, 120 meter is quite common. In fact, I have heard now it is more than 128 meter, 111 meter, 97 meter, 95 meters, and this is the 2.6 to 2.8 megawatt. Older windmills, many of them we have used in India, are more like done at around 50-60 meters, and that is about 1 megawatt. These are 2 megawatts. Rated power for 2.1 megawatt, and typically for both this I have given you. Operation wind speed range in which they operate. If wind speed is too low, the 1 megawatt will not even take off. Rated wind speed, rotor diameter, that is a rotor diameter. So, it has to be large. Of course, rotor diameter 97 meter, it has to be mounted at 120 meters or something like that. The voltage is 380 to 460, this is the lower voltage. There are some very interesting and simple formulas. Power of a wind stream is given by half into energy density of air 1.225 kg per meter cube, multiplied by the area swept on the rotor, multiplied by V cube. Area is pi r square, pi d by 2 whole square, multiplied by velocity q. So, if the velocity increases, even even to 1.1, what you will get is 1.1 into 1.1 into 1.1, and it is more like 1.35 or 1.4. If velocity increases by 20%, you are going to get about 75% more power. This is the wind power, this is the wind power, this is the wind power which is coming. Will all of it be converted? No. But if we increase by 20%, it goes up by 1.73 times. Now, the second important thing, the wind speed, which is the major V cube comes in, it keeps on increasing as the height increases. Of course, this is not forever, this is for up to a certain, maybe 120, 125, 130 meter. We know this formula is a curve fitting formula, where it says h by h0, height by some reference height to the power of alpha. Alpha is depends on various things multiplied by the velocity at h0. If velocity at, so velocity at some height is measured and velocity at another height is higher than that. That is the important factor. So, alpha varies from roughness to the terrain and could be 1 by 0.143 or 0.2. So, it increases, and remember that the power is increased by V cube. So, it has a huge impact if you increase the height. Finally, what is the power actually by the windmill? It depends on the what is called power coefficient, and can be as high as 0.5. So, 50% of the wind energy can be converted to power. Now, it does not mean that the rest of the energy is wasted. The wind will continue to flow, it has a lot of other role to play, but 50% is converted to power. That much wind will get slowed down, just like solar energy falling on a panel with 20% efficiency does not mean 80% energy is wasted. Okay. It is important because very often in common usage people think it is a poor efficiency, well it is a very good efficiency. For rural areas, alpha is approximately 0.2, and as I told you, wind speed increases 25% as you go from 10 to 30 meters, and if you go 60 meters 43%, and since the cube you can just determine what happens. And air density changes with temperature, small amount. With height also air density decreases. So, if it decreases, so you will have a negative factor, you will get less power, but less dense will produce about 10 to 20% less power, but height will give you higher velocity much more than this. You have to take the factor into account. So, typically it is not, there is a certain peak, the capacity factor. In a year, wind is not constant, it keeps on changing. Now, there is a peak power, peak output that you can produce when you get the best possible wind, and average output by peak output is called capacity factor. So, the wind is not constant. So, 30% of the time in a 365 days multiplied by 24 hours, you multiplied by the peak power of the windmill and multiplied by the capacity factor is actual energy produced per year multiplied by 1 hour. Now, what does this show up? Please remember this. Does this say that this is the typical wind frequency? Wind frequency. The wind frequency is mostly in a particular area between 5, 6, 7, 8, 9. It keeps on going up. So, you get all kinds of wind, but for very small percentage of time, and that is the average of this is around 30%. Average is around 30%. That is the average. That is what this says. So, annual wind production will be half into rho. Rho is the air density multiplied by the area swept multiplied by the V cube, the velocity at which you are operating. You can take the peak velocity multiplied by capacity factor, that is what you will get in a year, multiplied by the coefficient of efficiency, multiplied by 8760. Where does 8760 comes from? 24 into 365 or 360, I think, or 365, 24 into 365. This is the average wind power produced by an actual windmill. So, if it is a 2.1 capacity, you can take the 2.1 capacity and you can then calculate what it will be. So, this is what you see, that this is the for a particular mill, this is a power curve, the power produced as wind speed. It saturates. Why does it saturate? It is not supposed to produce more than 2 megawatt. The windmill is only 2 megawatt. So, it will saturate, and these are different windmills from different people, it saturates slightly differently. And for this particular windmill, this is shown as the power produced, and this is the efficiency. Why is the efficiency power efficiency? Because what happens is that beyond a certain wind speed, it saturates. Now, you may increase the wind speed, but now the efficiency will fall down. So, this is the efficiency, this is the efficiency, this is the peak efficiency, and then it will fall down. Why? Because you have reached the capacity, beyond that windmill cannot produce, and the power produced of course does not fall. Power producers hit close to 2000 kilowatt, 2 megawatt hour at the peak. There are a few other factors which need to take into account. What if there is an obstacle? Typically, the wind will move like this, wind will move like this. Now, as the wind move like this, in this area the wind will not be as strong, it will rotate like this. So, you typically take 10 meter above the tallest obstacle, and there within the 100 meters. So, if within the last 100 meter radius you want to take. So, this is the typical 2 h you would like to take. So, 10 times this 20 h and this is the tallest obstacle. So, you want to go above 10 meters above this. This is typically lots of data has been collected over here and found, and so windmills are kept away from obstacles. That is what it is done. Now, the question is one more issue that comes up. If it is a single windmill, there is no issue, what we have done is enough. What if you create wind farm? This is a typical wind farm. How closely can you put windmills? One may say one can put lots of windmills and you will get huge amount of power. Sorry, because one windmill will impact the power produced by the neighboring windmill. So, all neighboring windmill, why? Because they disturb the airflow. You may get, if it is a single windmill, you may get the best speed. Second windmill, you will not get, both of will produce less speed. So, there is a lot of work that has gone on, saying the windmill if it is facing like this, this should be a certain distance, and if there is one windmill, another windmill, if this is the direction of the wind, in the direction of the wind, they should be separated by say some n into d, and L perpendicular to this should be done by m into d, and here I have taken 5 and 10 as example. There is a lot of study that done here. This is m d and n d, this is the direction of the wind, m d and n d. Now, what should be the value of m and n? M can be typically 5 to 10 to not impact the power, and n can be 3 to 5. Recent study shows the losses are minimum, less than 10%, if m is equal to 10 and n equal to 5, yields maximum capacity of 5 megawatt hour per square kilometer, considering d to be 90. If I take d, d is what? D is the diameter of the turbine. There is lots of different studies, and that tells you what is the maximum power, wind power that you can generate in the country. Of course, there are people 5D, 7D, but there are other windmills which seem to be working at very good at 3D, 5D. So, with this configuration and wind power at 100 meter, you can actually calculate in different areas what is the power produced, possible power produced in the whole of India. You convert it into windmills at either 3D, 5D or 5D, 7D, leaving out the urban areas. And what we have found, the 3D, 5D layout, most optimistic estimate produces 13.3, and if you find with the wind speed, actually wind can be power can be gainfully produced in Tamil Nadu, Andhra Pradesh, Telangana, Karnataka, Rajasthan, Gujarat and Maharashtra. Mostly if you see, most of them are coastal, or of course, Karnataka is not exactly coastal and Rajasthan is not coastal, but not too far away from coast and Maharashtra. So, this is with this is the potential wind speed. So, if you see, these are places where is 6 to 7 yellow color, 6 to 7, other places less it will not be so good. At 120 meters you get even higher, 7 to 8 you start getting. So, this is the area, this is the area, this is the area, small amount here, not much here. Okay. This is 100 meters, this is 120 meters, and when this is another one. Therefore, one sort of said that how much can be produced per annual grid cell. You divide into small cells and you 0.1 degree by 0.1 degree in terms of latitude, longitude, and then you say these are places where above 1000, these are places close to 1500, these are places where around 2000 can be produced. So, actually you can also produce it to some extent in Assam, some amount here, not bad, the rest of the country is poor. Here also it is concentrated this place, a little bit on this side. So, total land area has been ranked, rank 1, rank 2, rank 3 in terms of what is the percentage that you can produce, and there is one estimate that you can actually produce only 153 gigawatt. But there are other estimates which have gone to say is 16,000 gigawatt for solar and 3,102 for wind. Are this is only on land area, not taking the ocean into account. Are these reasonable? My feeling is they are little bit less, actual is more, because I think all these were done when windmills were mostly at 100 meters, now it is 120 meters, you are deploying it, it is higher, solar also efficiency has gone up. So, we have huge capacity, not just 20,000 gigawatt, I would say higher than that. That work continues, I do not think that we need to worry about, and there is a very good global wind atlas available. You can just say global solar atlas or global wind atlas, it will be able to tell you where how much wind is produced and what will be the area that can be done. And these are the again parts of a windmill. How much do they cost? If you want to do R&D, see, to a tower will cost you 23%, 26%. Wind blade. So, this is a very good thing, that what is a converter cost is only 5%, where the money is, and then you can calculate cost per kilowatt hour. To calculate cost per kilowatt hour, you have to take all this into account. It is a very nice diagram I saw. From this wind turbine and installation, you will have to calculate the operation and maintenance cost, the actual cost, price of turbine, foundation and road construction. From there you derive per annum cost using what? depreciation and interest, and from there you derive the lifetime of the total cost. So, this is the capital cost that comes in. From here you can calculate the capital cost. Of course, to do this you have to take into account rotor diameter, hub height, mean wind height to compute the kilowatt. So, this is how you start, find out the costs, then this is the operation and maintenance cost per year. This together will give you a total cost, and then this is the total will give you how much energy you can produce, and then you can calculate energy per kilowatt hour. This is exactly what I expect you to be able to do. This is a typical number, used to be between 4.5 to 6.85 per crores per megawatt. It has actually gone down. This is the number that used to be there, and that we would have given you around 2 rupee 50 paise. Today the cost is less than 2 rupee 50 paise per kilowatt hour. One can do detailed costing and detailed economics, just like what we did. You have to take into account installed capacity, investment, expected generation, and then you can calculate the depreciation interest over so many years, and you can see how much return will you get. This is, by the way, seasonal variation of wind. This is a big problem for wind, solar, everything. Solar is more or less constant, not bad. Wind typically 4-5 months, and then of course, it falls down out here. Then there are others which produces less, but you can then calculate the total. Does it give you total also? No. This is wind, this is solar. There are other things like Bucksy, small idle is this. There are others which give you this, Bucksy which gives you this. Biomass also gives you biomass, you can see the curve. So, this will also give you some idea. Well, that is pretty much it.